All right, hello everyone. These are the video solutions for the chapter 2 to 3 Troy High AP Chem practice test. We're gonna get straight into it. It says try to use mental math for the multiple choice problems. You can kind of just disregard that. Um, I'm not gonna go through these first three problems. They're just sig figs. Let's really start with number four. Obviously, the answer to this is E, B, and then A. But let's start with number four. Manganese makes up 1.5 times 10 to the negative 4% by mass. It's asking how many grams of manganese would be found in the body of a person weighing 80 kilograms. So for that, we're given 1.5 times 10 to the negative 4%. So if we write that as like without scientific notation, it's going to be 1.4. We can quickly like kind of change it. We can do 1.5 times 10 to the negative 4 in our calculator. Make sure we're in normal mode and then just click enter. And it's going to give us how many decimal places. So it's going to be 0.00015%. Remember that when we had to convert percents to decimals, we have to divide by 100. So in reality, this is this percent divided by 100 to get into a decimal, or this divided by 100 to get into a decimal, which is going to be 1.5 times 10 negative 6. So what that tells us is that 1.5 times 10 negative 6, that's the decimal proportion of manganese in the body. We can multiply that by the weight of the body to find out how much manganese is going to be there. Notice it's 80 kilograms, so we're going to have to convert this to grams. So 80 times 1,000. So we do this, we're going to get 1.2 times 10 negative 1 grams. So the answer is going to be E, one of these. 5 zinc metal reacts with iron 3 oxide. So iron 3 oxide, let's quickly write the formula for that. That's going to be Fe2O3 to make metallic iron and zinc oxide. So Fe2O3 plus Zn reacts with that to form Fe plus zinc oxide, ZnO. We quickly balance this. Uh, that's our equation. It says how many moles of iron 3 oxide are required to form 1 mole of zinc oxide. So as we can see from our balance equation, we need to form 1 mole of zinc oxide. We're going to need 1/3 of a mole of Fe2O3 because it's a 1:3 ratio. If we put it in 1 mole of Fe2O3, we get 3 moles of ZnO. So if we only want 1 mole of ZnO, we only need 0.333 moles of Fe2O3. So the answer is A. Next up, it says select the correct formula for the compound disilicon tetraphosphide. So this is a naming problem. Disilicon, that's di, so that's Si2. Then tetraphosphide, that's FCP4. So Si2PO4, that's going to be A. Next, select the correct name for the formula H2CrO4. Notice that this is an acid. CrO4 minus 2 is a polyatomic ion. Then when you add hydrogen ions to it, it's going to form the acid H2CrO4. And the polyatomic ion is chromate, so it's going to become chromic acid because H goes to ic acid. So the answer is B. Next up, 8, select the correct formula for aluminum acetate. Aluminum, look at the periodic table, it's going to form +3 charge. Acetate, remember, is C2H3O2 minus. So in order to balance this out, we're going to need 3 acetate ions to form Al, and then C2H3O2 and 3. Obviously, we need 3 negative charges to balance out the +3. So this is the correct formula. And that is consistent with the answer choice A. Next up, FeX3 contains 12.62% iron by mass. Determine the identity of element X. So we can say that the mass of iron, which is 55.85 grams, divided by the total mass of the compound, 55.85 plus 3 times the molar mass of X, which we don't know. So I'm just going to call it 3 times mmx. It's 3 because there's 3 X's in FeX3. And then times 100, that's going to equal the percent, so 12.62. So now we can just solve for mmx, like how we'd solve for a regular old variable. We can do 12.62 divided by 100. Multiply that by this whole thing. Um, so we'll get 55.85 equals 0.1262 times 55.85 plus 3. I'm just going to call it x now. instead of molar mass of X. Then we kind of just divide 0.1262 on both sides. So we get 442.55 equals 55.85 plus 3x. Now we obviously just do minus 55.85 minus 55.85. And then we divide that quantity, 386, 386.7 equals 3x. So divide that by 3, divide that by 3. We get 128.9. So that's pretty consistent with answer choice E because the molar mass of iodine is around 126.9. So iodine is pretty close to that. Naturally occurring copper exists in two isotopic forms. The atomic mass of copper is that. What is the approximate natural abundance of copper 63? So for this problem, we know that the mass of one isotope, so 63 for copper 63, times its abundance, we can call it X. Call it 63 times X plus the abundance, or the mass of copper 65 times the abundance of it. That's going to equal the molar mass of copper. So 63.55, or atomic mass, 63.55 AMU. So we have two variables, but we only have one equation. So we're going to need another equation to set up a system of equations. We know that X plus Y must equal to 1 because these are both proportions. And it says it only exists in two isotopic forms. So we know that this as a decimal and Y as a decimal, they're going to add up to 1. You can also think of them as percents. X as a percent and then Y in percent form, it's going to add up to 100%. So we can kind of just solve for this system. If we do 63x plus, if we subtract x from both sides, we get y equals 1 minus x. We're going to do 65 times 1 minus x equals 63.55. So that means 63x plus 65 minus 65x equals 63.55. So that means negative 2x equals, we subtract 65 from both sides, negative 1.45. So we divide negative 2 by on both sides. We get x, or we get x equals 0.725. So that means it's 72.5% copper 63. Remember, we assigned copper 63 the abundance x. So I'll multiply this by 100 to get into a percent. So it's around 72.5%. So that's consistent with answer choice E. Next up, phosphoric acid. Reaction of sulfuric acid with phosphate rock according to the equation, right? So it's carried with 103 grams of calcium phosphate and 75 grams of sulfuric acid, which substance is limiting. So obviously, it's going to be limiting reagent. That's one of our reactants. So we can immediately eliminate phosphoric acid and calcium sulfate because those are the products, not the reactants. So let's quickly calculate the molar masses of calcium phosphate and sulfuric acid. Calcium phosphate, that's 3 calciums, so that's 40.1 per calcium, so that's 40.1 and times 3 plus phosphate. Phosphate, there's 2 phosphates, so, and then phosphate is going to be 30.974 for the phosphorus plus the 4 oxygens. So it's 4 times 16. Give me the molar mass of phosphate, or sorry, for calcium phosphate. So 30.974 plus 64 times 2 plus the calcium molar mass we calculated, which 120.3 in total. That's going to be 310.248. So if you have 103 divided by 310.48, that means we have 0.33 moles of calcium phosphate to start with. Calculate how much sulfuric acid we have. You have 75 grams of it. Sulfuric acid, that's going to be 2 times 1 for the 2 hydrogens plus the sulfur and the 4 oxygens. So 32.06 for the sulfur and plus 64 for the 4 oxygens. So that's going to be a molar mass of 98.06. Divide 75 divided by 98 0.06. That means we have 0.765 moles of H2SO4. Now to find which one is limiting, again, we divide the molar amounts that we got by their molar coefficients in the chemical equation. The molar coefficient of calcium phosphate in the equation is just 1. So we just do 0.33 divided by 1 is just 0.33. Okay. Then 0.65 divided by 3 for the coefficient of 3, it's going to be 0.25. So obviously 0.25 is less than 0.33. So that means sulfuric acid is limiting reagent. So the answer is D. 12, strong heating of 7.534 grams hydrated calcium sulfate. So calcium sulfate, obviously CaSO4, and then it's hydrated. So that means it has water molecules trapped inside the ionic compound. And there's obviously a certain amount of water molecules, and that can be represented with the molar coefficient X and then H2O. So um, when you heat it, it's going to drive off all the water. So it's going to form CaSO4, and then water is going to obviously come out as gas. So that means the mass of anhydrous, just meaning without water, um, calcium sulfate, that's going to be this mass. And then it says, what is the ratio of water molecules to calcium sulfate units in the hydrate? We're given the mass of the entire hydrate and then the mass of just the anhydrous sulfate, yeah, anhydrous calcium sulfate. So that means 7.534, which is the total mass minus the mass of the anhydrous calcium sulfate. So just the calcium sulfate, that's obviously going to get us the mass of the water that we drove off. So 7.534 divided by minus 5.957. It's going to be 1.577. So that means there's 1.577 grams of water that we drove off when we uh, heated up the hydrated calcium sulfate. Obviously, 1.577 divided by 18. That'll get us the amount of moles. 0.0876 moles. That's how many moles of water we drove off. So just looking at our answer choices, you can see that if we had 0.0876 moles of water, we can calculate the amount of calcium sulfate we had by doing 5.957 divided by molar mass of calcium sulfate. So that's going to be 40.1 plus 32.06 plus the 4 oxygens from sulfate, so 4 times 16. That's going to be 45.1 plus 34, 5.957 divided by that. It's going to be 0.04375 moles CaSO4. We can compare this quantity to this quantity to find the molar ratio. We can clearly see um, if we divide 0.0876 divided by the smaller molar quantity, which is the calcium sulfate, 0.04375, and we divide 0.04375 divided by 0.04375. We're doing this to calculate the molar ratio. It's going to be 2 to 1. That means there's 2 moles of water for every 1 mole of calcium sulfate. Now, in the problem, it doesn't show it like that. It obviously just shows the answers. So you can kind of just use the answer choices and calculate some of them out to find the ratio. Obviously, we know that the first step we subtracted molar masses, so that's probably going to be the first step in our calculations as well. So we're going to eliminate B, C, and E. So it has to be either A or D. And then obviously the moles of calcium sulfate, we found that the molar mass of calcium sulfate was 136.16, and there was 5.957 grams of it. So we can say that we did this equation. If you calculate all this out, we'll get the same answer of 2. So the answer is A. Number 13, a reaction occurs between sodium carbonate and hydrochloric acid. Correct set of coefficients. Okay, so sodium carbonate, Na2CO3, hydrochloric acid, H plus, and then CO minus, so HCl. It's going to form NaCl and carbon dioxide and water. Quickly balance this. put a 2 because there's two sodiums on this side, only one on this side, so we put a 2 there. We're also gonna have to put a 2 next to the hydrochloric acid to balance out the chlorines. Notice how that also balances out the H's, and notice how the carbons and the oxygens are already balanced. So the answer is for this is going to be 1, 2, 2, 1, 1. So it's going to be B. 14, the Claus reaction is used to generate elemental sulfur from hydrogen sulfide, right? So this is how much sulfur in grams is produced from 48 grams of oxygen. If you have 48 grams of oxygen, that's O2, remember? Because we have O2 in the equation. So 48 divided by the molar mass of O2, that's just going to be 16 times 2, 16 for each elemental oxygen. So that's going to be 1.5. We start with 1.5 moles of oxygen. And we know that for every 3 moles of oxygen, we're producing 2 moles of sulfur dioxide. And we know that for every 1 mole of sulfur dioxide, we're producing 3 moles of S. So we can say that for every 48 grams O2, well, for every 32 grams O2, we have 1 mole O2. And then for every 3 moles O2, we have 2 moles of SO2. And for every 1 mole, 1 mole of SO2 that we have 3 moles of S. And we have that for every 1 mole of S, we have 32.06 grams of S. Um, so if we kind of multiply all this out, 48 times 2 times 3 times 32.06 divided by 32 divided by 3, that's going to be 96.18 grams. So that's going to be consistent with answer choice D. All right, moving on to number 15. How many grams of H2O will be formed when 32 grams of hydrogen gas mixed with 2 grams of oxygen gas and allowed to react to form water? So H2 plus O2, it's forming water. Make sure to balance it. So put a coefficient of 2 here, but coefficient of 2 here. 32 grams of hydrogen gas, 32 grams of oxygen gas. We know that oxygen gas has a molar mass of 32, so that means we essentially have 1 mole of oxygen gas, 1 mole of O2. 32 grams of hydrogen gas, that's H2, so molar mass of 2 grams per mole. That means we're going to have 16 moles of hydrogen gas. Divide these by their molar coefficients in the equation. Divided by 2, divided by 1, check quantity is smaller. This is 8, this is 1. Obviously, the oxygen is limiting. So we set up our stoichiometry. 32 grams O2. Well, for every 32 grams O2, we have 1 mole O2. For every 1 mole O2, we have 2 moles water. And for every 1 mole of water, we have 18 grams of water. If we multiply all this out, 32 times 2 times 18 divided by 32, it's going to be 36 grams. So the answer is C. 16 and 56 grams of lithium reacts with 56 grams of nitrogen. Lithium nitrate is obtained. So you have lithium. You have nitrogen. Remember, nitrogen is diatomic, so Li plus N2. It's going to form lithium nitride. Lithium. So nitride is the N minus 3 ion. Lithium is the plus 1 ion. So we're going to need 3 lithiums to form lithium nitride. So it's going to be Li3N. So it's going to be Li3N. To balance this, we're going to need 2 lithium nitrides to balance out the nitrogens, and then we're going to need 6 lithiums to balance out the lithiums. So 56 grams of lithium, 56 divided by the molar mass of lithium, which is going to be around 6.94. So if we do 56 divided by 6.94, that's going to be, we have 8 moles of lithium, 56 grams of nitrogen. Nitrogen, remember, is diatomic, so 14 times 2 for the molar mass of nitrogen gas. 56 divided by 28 equals 2. So that means we have 2 moles of N2 and 8 moles of lithium. Remember, divided by the smaller, divided by the molar coefficient. So this is divided by 1. This is divided by 6. So 8 divided by 6. That's going to be 1.33. 2 divided by 1 is just 2. This quantity is smaller than 2. So that means lithium is limiting. It's limiting reagent, Lr. So that means for every 56 grams of lithium, well, for every 6.94 grams lithium. We have 1 mole lithium. And for every 6 moles of lithium, we have 2 moles of lithium nitride. And for every 1 mole lithium nitride, how many grams of lithium nitride do we have? Well, 3 lithiums, that's going to be 6.94 times 3, plus molar mass of nitrogen, which is going to be 14. So 3 times 6.94 plus 14, it's going to be 34.82. So grams of lithium nitride. So we multiply all these numbers on the top. We're going to get 93.65 grams. Remember, it says a 50% yield, so we're going to multiply this by 0.5. That's going to be 46.8 grams. That's around 47 grams. So the answer is C. Next up, let's go to number 17. The following two reactions are important in the blast furnace production of iron metal from iron ore. Says how many moles of oxygen are required for the production of 5.58 kilograms of Fe? So 5.58 kilograms of Fe. 5.58 kilograms of Fe. We know that for every 1 kilogram of Fe, we have 1,000 grams of Fe. And we know that for every 55.85 grams of Fe, we're obviously going to have 1 mole of Fe. And we know from the balance equation for every 2 moles of Fe, now be careful here, for every 2 moles of Fe, we have 3 moles of carbon monoxide. So 3 moles CO. And we know that for every 2 moles of CO, we have 1 mole of O2. So that's our stoichiometry. 5.58 times 1,000 times 3, and then divided by 55.85, divided by 2, divided by 2. So it's around 75. So the answer is B. 18. 122 grams propane, 128 grams of oxygen. So propane, just as a reminder, that's going to be C3H8. So it says C3H8, and we're doing a combustion reaction. So that means we're going to do hydrocarbon plus oxygen to form carbon dioxide and water. So CO2 plus H2O. To balance this out, we're going to need 3 carbon dioxide molecules because 3 carbons, and then 4 hydrogens, 4 water molecules to balance out the hydrogens. Notice now that we have 6 oxygens on this side, and then plus 4, so that's 10 oxygens on this side of the equation. So we're going to need 10 on this side. So we're going to do that by adding a molar coefficient of 2 for the oxygen, O2 gas. That means we're going to get 10 moles of oxygen in total. So that's fully balanced. Now we can do the calculations. 22 grams of propane. So 22 divided by molar mass of propane, that's just going to be 3 times 12 for the molar mass of carbon, plus 8 times 1 for the molar mass of hydrogen, so that's just 8. So 3 times 12 plus 8, right? 22 divided by 44, that's going to be 0.5 moles propane, okay? And for oxygen, 128 grams of oxygen divided by the molar mass, 32. It's going to be 4. So we have 0.5 and we have 4. So divide by the divide by the molar coefficients. So this is going to be divided by 1. It's going to be divided by 5. So 4 divided by 5, that's going to be 0.8. And this is going to be 0.5. So clearly propane is limiting. So we know that for every 22 grams propane, so C3H8, well, we know that we have 44 grams of propane, then we'll get 1 mole of propane. And we know that for every 1 mole of propane, we'll have 3 moles of CO2. We're asking for water, so we'll have 4 moles of H2O. And we know that for every 1 mole H2O, again, we want to end in grams of water, so that means we're going to do 18 grams water. So now we just multiply out. 18 times 4 times 22 divided by 4. It's going to be 36. So it's 36 grams. So it's going to be answer choice E. Next up, we have this reaction right here, saying how many grams of HCl required to react with 170 grams, as 174 grams of MnO2. So MnO2, let's quickly just do the stoichiometry. If you have 100, you have, I'll erase this. So you have 174 grams of MnO2. Well, we know that for every how many grams of MnO2, let's first calculate the molar mass of MnO2. So that's going to be molar mass of magnesium plus two oxygens. So molar mass of magnesium, that's 54.938 plus the two oxygens, so 2 times 16. So 2 times 16 plus 54.938. That's going to be 86.938. 86.938. We know that for every 86.938 grams of MnO2, we have 1 mole of MnO2. And we know that for every 1 mole of MnO2, we're going to need 4 moles of HCl. And converting that to grams of HCl, we know that for every 1 mole of HCl, we just have the molar mass of HCl, so that's going to be hydrogen, so 1.01, and then plus 35.45 for the chlorine. It's going to be around 36.46. We have 36.46 grams of HCl. So I'll multiply all this out. 174 times 4 times 36.46. Divide that by 86.938. And then that'll be our answer. So that's 292 grams. So that's an E. And then number 20, it says how many grams of CO2 can be prepared from the reaction of 43.5 grams of MnO2 and 36.5 grams of HCl. We know that 36.5 grams of HCl, that's basically 36.46. So we essentially have 1 mole HCl. And then 43.5 grams of MnO2, we can kind of just eyeball this from the molar mass of MnO2 and say this is half a mole of MnO2. So 0.5 moles MnO2. So we have the molar quantities. Now let's divide it by the molar coefficients from the equation. Divide 0.5 divided by 1. Divide 1 divided by 4. So we get 0.25 and then 0.5. Obviously, this quantity is smaller. So that means HCl is a limiting reactant. So Lr is over here. So we know that 36.5 grams HCl. Well, we know that for every 36.5 grams HCl, we'll have 1 mole HCl. And we know that for every 4 moles HCl, we'll have 1 mole of Cl2. Actually, yeah, we'll have 1 mole of Cl2. And then we know that for every 1 mole Cl2, let's calculate the molar mass of Cl2. That's just 2 chlorines. So it's going to be 35.45 times 2. So that's going to be 70.9. 70.9 grams Cl2. So now we're in the correct units. Let's just multiply all this out. Times 36.5 divided by 36.5. That's going to be 17.7. So around 17.8 grams. That's going to be 20. 20 is going to be C. Hydrochloric acid can be prepared by this reaction. It says how many grams of HCl can be prepared with 2 moles of sulfuric acid and 117 grams of sodium chloride. So let's first calculate the molar mass of sodium chloride. That's going to be 22.99 for the sodium, and then plus 35.45. 35.45 for the chlorine. That's 58.44 grams per mole for sodium chloride. So let's do 117 divided by 58.44. That's going to be around 2. So you have 2 moles of sodium chloride and 2 moles of sulfuric acid. Let's divide each quantity by their molar coefficient. So in sodium chloride, the equation, the molar coefficient is 2, so 2 divided by 2, that's going to be 1. Then 2 moles of sulfuric acid, the coefficient is 1, so 2 divided by 1, that's going to be 2. Obviously, 1 is less than 2, so that means sodium chloride is the limiting reactant. So now we can do our stoichiometry. You know that for every 117 grams of sodium chloride that we started with, well, we know that for every 58.44 grams of those, we'll have 1 mole of NaCl. And we know that for every 2 moles NaCl, we'll have 2 moles of HCl. And we know that for every 1 mole HCl, how many grams of HCl do we have? It's going to be molar mass for HCl. That's just going to be 36.46 grams. Now let's do our multiply out our stoichiometry. 117 times 2 times 36.46. Then divide that by 2, divide that by 58.44. So we're going to get 73 grams approximately. So the answer is going to be B. 22, what is the theoretical yield of chromium that can be produced from a reaction of 38 grams of chromium 3 oxide with 18 grams of aluminum? Right. So 38 grams of chromium 3 oxide, that's going to be Cr2O3. Let's calculate the molar mass of that. It's going to be 2 chromiums. So 2 times 51.996, the molar mass of chromium. So that's 3 reactions. So that's 3 times 16. This is going to be the molar mass of chromium 3 oxide. So it's going to be times 51.996 plus 48. That's going to be 151.992. I'm just going to round that to 152 grams per mole. We're given 38 grams of it, so 38 divided by 152. That means we have approximately 0.25 moles of Cr2O3. And it says 18 grams of aluminum, so that's just Al. So 18 divided by the molar mass of aluminum, which is just 27, or around 27. It's 26.982. So 26.982. It's going to be 18 92. It's going to be 0.667 grams per mole. Sorry, just grams. No, this should be moles of aluminum. This is moles of chromium 3 oxide. Then we divide these molar amounts by their coefficients in the chemical equation. So molar mass of the coefficient of aluminum is 2, so divide this by 2. Coefficient for chromium 3 oxide is just 1, so it's going to be 0.25 compared to 0.667 divided by 2, so it's 0.333. So clearly 0.25 is less, so that means Cr2O3 is limiting reactant. So we can set up our stoichiometry. Started with 38 grams of Cr2O3, and we know that for every 152 grams, we have 1 mole of it. And we know that for every 1 mole of Cr2O3, we're going to have 2 moles of Cr. And we know that for every 1 mole of Cr, we're going to have 51.996 grams of Cr. So now we're in the correct unit. So let's multiply out. 51.996 times 2 times 38, divided that by 152. It's going to be around 25.98 grams. So we can say that's around 26 grams. So the answer is B. Moving on to number 23, consider the following reaction of hydrogen gas with oxygen gas. It's an incomplete reaction, which of the following diagrams represents the amount of products and reactants left over the reaction. So this is a limiting reactant kind of style problem. O2 is represented by these dark circles, hydrogen gas by these light circles. Let's find the limiting reactant. So by just calculating the number of moles, we can kind of just represent each one of these molecules as number of moles. So you have 3 moles of O2, and we have 1, 2, 3, 4, 5, 6, 7, 8 moles of H2. So 8 moles of H2 and 3 moles O2. We know that they react in a 2-to-1 ratio, so divide this by 2, divide this by 1. So that means 4 and then 3. 3 is less than 4, so that means O2 is a limiting reactant. So that means after our reaction is done, that means we should have some H2 left over because it's in excess. So we can eliminate A. We can also eliminate no the answer choices because they all have H2 left over. But we know that if we have 3 moles of H2, or sorry, 3 moles of O2 and it's limiting, well, we know that for every 1 mole of O2, we have 2 moles of water produced. So if we have 3 moles of O2, that means 6 moles of water must be produced. So let's check our diagrams. Which one has 6 moles of water? This one has 1, 2, 3, 4, 5, 6, right? That's correct. 1, 2, 3, so this is incorrect. And this has 1, 2, 3, and some oxygen left over and hydrogen left over. So this is wrong. So it has to be B. This is correct because it has hydrogen left over, and more specifically 2 moles of hydrogen left over. So in this reaction, for every 3 moles of O2 that are consumed, double as much hydrogen gas is going to be consumed. So that means 3 moles of O2 is consumed. That means 6 moles of H2 is consumed. So this is going to get consumed, this is going to get consumed, this is going to get this. So that means there's only 2 moles of H2 left over, which is consistent with what we see in the diagram. So the answer is B. Number 24, which of the following represents a pair of isotopes? Isotope just represents same number of protons or same atomic number, but different mass numbers because different number of neutrons. So we can eliminate A, since this is 6, this is 7. B, this is 6 and 14. C, 6 and 14. D is the only correct one, 7 and 7, because they have different mass numbers. So um, this would represent nitrogen, uh, nitrogen 13, which is an isotope, and then nitrogen 14, which is another isotope. So these are two isotopes. They have the same protons, same atomic number, but different mass numbers, and therefore different neutrons. Because remember, mass number is just the number of neutrons plus protons. 25, the mass of element Q is found in 1 mole of each of the following compounds: 38 grams, 57 grams, 76 grams, and 114 grams, respectively. Possible atomic weight of element Q is what? I like this problem a lot. It's kind of like out of the box. Just kind of eliminating answer choices. If you look at the periodic table, there's no atomic element with the weights 12.7 or 57 or really 38 or really 27.5 for that matter. The only one is fluorine, which is 19. But to really solve this, notice that all these masses are multiples of 19. So 38, that's obviously 2 times 19. 57, that's obviously 3 times 19. 114, and then 76, obviously all multiples of 19. So this could represent, like, for example, uh, in a compound, it could be something like Fe, then F2. That'll be iron 2 fluoride. That's going to have two fluorine atoms, each of which is 19. So the total mass of fluorine in this compound is going to be 38 grams. Another one would be something like FeF3. So it's going to be iron 3 fluoride. Obviously, that's going to be three fluorines, each of which has 19. So that's going to be 57 gram fluoride, and so on. So we know that the element is going to be fluorine because the common multiple between all these is 19. So that means the molar mass of the element Q is going to be 19 grams per mole. And that's consistent with what we see on the periodic table because there is actually an element with that many grams, which is fluorine, 19 grams per mole. So the answer is B. 26 is 27-gram sample of an unknown hydrocarbon was burned in XX oxygen to form 88 grams of carbon dioxide and 27 grams of water was a possible molecular formula of the hydrocarbon. So let's just quickly look at what it's saying. So obviously hydrocarbon, we can call it CXHY. We don't know the formula. Plus oxygen is going to be an excess. It's going to form CO2 and H2O. Looking at the balanced equation, you can see that all the carbons in this reaction on the reactant side come from this hydrocarbon. So that means this coefficient, CX, must be consistent with X next to the C. For Y over here, we should have Y over 2 for the molar coefficient of H2O, because then we'll have Y amount of hydrogen on this side of the equation and Y amount of hydrogen on this side of the equation. Is Y over 2 and then times 2 is going to just be Y. So it says 88 grams of carbon dioxide was formed. 88 divided by the molar mass of carbon dioxide, which is 44. It's going to be 2 moles of carbon dioxide that formed. So 2 moles of carbon dioxide formed. And we said that that'll be the coefficient for X. So that means this is C2. And then it says 27 grams of water. 27 grams of water. 27 divided by molar mass of water, that's 18. So 1.5 moles of water was produced. And that 1.5 equals Y over 2. So that means Y equals 3. So it's going to be C2H3. Look at the empirical formulas. This is the empirical formula. Remember, we need the molecular formula. And the only one with the same molar ratio is going to be D. So the answer is D. All right, number 27, it says a bathroom type scale is calibrated, marked off in tenths of a kilogram. Bathroom type scale, I'll throw a picture on screen of what it kind of means by bathroom type scale. It's just like a scale like that you'd find at your house. It says it marked in tenths of a kilogram for 1 to 200 grams, 200 kilograms. So it reads stuff like 1.1 kilograms. It'd read something like 187.1 kilograms, things like that. It says how many significant figures should be used to express the mass of anyone using scales mass between 10 and 99 kilograms. So it'd read something like 10.1 and like 87.1 kilograms, stuff like that. But it's a bathroom type scale, and you kind of estimate the in-between points. So you're going to use one sig fig past the decimal, or past how many you have. So instead of 10.1, it's going to be something like 10.15. It could also be 10.16, and you use that based on your estimation on where the needle is on the scale. So notice how this is going to be 4 sig figs then. So that means the answer is B. 28, what number of moles is O2 is you need to produce 14.2 grams of P4O10 from P. The mole mass of P4O10 is 284 grams per mole. So if we balance out the rewrite the equation, so P plus O2 makes P4O10. Let's balance it. We're going to need four phosphoruses and then five O2 molecules get bounced on both sides. So 14.2 grams of P4O10. It says that 284 grams per mole is the molar mass. So 14.2 divided by 284. Calculate that. 14.2 divided by 284. It's going to be 0.05 moles of P4O10 that you're producing. And we need 5 moles of O2 for each mole of P4O10. So we're going to need 5 times as much. So 0.05 times 5, that's going to be 0.25 moles of O2. So that means the answer is going to be D. Now, next up, 29. What is the balance equation for this reaction? What is the limiting reactant? Obviously, the limiting reactant is going to be the one that's not in excess. Look at the products. You can see that the red is in excess because there's some leftovers. That's O2. So that means the limiting must be the other reagent, so NO. So that means the NO is limiting. So we can kind of eliminate some answer choices. Eliminate E, C. So it has to be either B or D. If you look at the balanced equation, we can kind of write this ourselves. It's going to be NO plus O2 reacting to form NO2. Notice, if you try to balance this, I'm going to put coefficient of 2 here, coefficient of 2 here. That's going to be balanced. So the answer is going to be D. Next up, 1 gram sample of limestone, which is mostly calcium carbonate. So basically, limestone, just a rock, right? A lot of calcium carbonate in it. It's dissolved in acid, and this many grams of carbon dioxide was generated. So it says what percent of calcium carbonate by mass is in limestone. So when we're doing percent mass like this, we just want to do the mass of the thing that we're interested in this case, mass of calcium carbonate. So mass calcium carbonate divided by the total mass of the sample that we used. We have a 1 gram sample. So mass calcium carbonate divided by 1 times 100. That's going to be making it into a percent, and that'll be our answer. So all we got to do is find the mass of calcium carbonate. We can do that by doing the molar ratio with the amount of carbon dioxide. So 0.22 grams carbon dioxide. We know that for every 44 grams of carbon dioxide, that's the molar mass of carbon dioxide, we're going to have 1 mole of carbon dioxide. We know that for every 1 mole of carbon dioxide, we're obviously going to have 1 mole of calcium carbonate. And for every 1 mole of calcium carbonate, we have a certain amount of gram calcium carbonate. If we calculate the molar mass of calcium carbonate, we see that it's around 100 grams per mole. So we can just say 100 grams. So multiplying all this out, 0.22 times 100 divided by 44. So that's around 0.5 grams. So that's the mass of calcium carbonate. We can put that in. So 0.5 divided by 1 times 100. That's obviously just going to be 50%. So the answer is going to be B. Next up, 31. It's found that the 3 grams of M reacts with 1 gram of oxygen to form the compound ML3 times the weight of M is what? So solve this problem. Kind of eliminate some answer choices at first. Obviously, answer choice A, 16 AMU, that's the molar mass of oxygen. O, then O3 isn't really going to make any sense. So I think we can kind of eliminate A. But really, 3 grams of M, so 3 over the molar mass of M. Notice how there's a 1 to 3 ratio between oxygens and the metal, or the element M. It says 1 gram of oxygen, so 1 gram of oxygen divided by molar mass of oxygen, that's 1 over 16 equals 1 over 16. And then time, there's 3 of them. So 1 divided by 16, that's 0.0625 moles. And notice there's a 3 to 1 ratio, so that means divide this by 3, that's going to get us 0.0208 moles. This is going to be the amount of moles of M. So if 3 over the molar mass equals 0.0208, we can just rearrange to solve for the molar mass. We multiply both sides with the molar mass times mm. So 3 equals 0.0208 mm. Divide both sides by 0.028. And we get molar mass is 144. So the answer is going to be E. 32, this is a systematic name for CrSO3. This is going to be the Cr. And then SO3, that's SO3 minus 2, that's going to be sulfite. Notice that's minus 2, so that means the chromium is going to be plus 2. That's going to be chromium 2 and sulfite. So the answer is going to be B. Next up, this is a systematic name for Cr2O3. Cr2O3. To make Cr2O3, we needed what? We needed three oxygen ions, anions, which is -2 charge, and then two Cr ions. We don't know the charge of the Cr, but we can see that this side of the equation must be neutral because this side of the equation is neutral. This is a -6 charge in total, so that means this must be +3 charge because 2 times +3 is +6, and +6 and the -6 will neutralize each other. So that means each chromium has a +3 charge. So this is going to be chromium 3 oxide. That's going to be A. 34th correct name for NH4NO3. That's going to be the ammonium ion, and then the nitrite or nitrate ion. So it's going to be ammonium nitrate. So the answer is D. It's 35. The correct name for BaOH2. That's just going to be barium and hydroxide since it's an ionic compound. So because OH minus, that's hydroxide, it's polyatomic ion. It's coming together with the Ba+2 ions. Remember, Ba forms +2 ions because it's in group 2 of the periodic table. 36th correct systematic name for KHCO3. Obviously, this is potassium, so we can eliminate all the other answer choices that have calcium. It's not A, it's not D, it's not B. It has to be either C or E. This is HCO, this is K plus, and then HCO3. This is the bicarbonate polyatomic ion, or also known as hydrogen carbonate. That's consistent with answer choice E, so it has to be E. It's not C because potassium carbonate, that would just be K2CO3. That'd be the CO3 minus 2. But instead it's HCO3 minus, so it's potassium bicarbonate. 37, select the correct name for NiS2O3. S2O3 minus 2, that's the thiosulfate ion, polyatomic ion. And then it's going to be with Ni in a 1:1 mole ratio. That means it's Ni plus 2. That's going to be nickel and then 2 thiosulfate. So it's going to be answer choice C. So after that, 38, H2CO3, this is going to be an acid, H2CO3. This is going to be carbonate ion, CO3 minus 2, plus the hydrogen ions to form H2CO3. So carbonate, remember 8 goes to ic acid, so 8 is going to go to carbonic acid. So the answer is C. Select the correct name for S2O4. S2O4, this is going to be a typical non-metal covalent compound. It's going to be sulfur, and then tetroxide. It's going to be D. Choose the correct formula. By this, it means like which formula is consistent with the ion charges. So for example, ZnCl, this is wrong because Zn is +2. So when it forms ionic compounds with chlorine, which is a -1 charge, it's going to be ZnCl2 instead of just ZnCl. So we know B is wrong. Same thing with Ag. Ag forms always +1 charge, and then chromate, that's obviously the polyatomic ion -2 charge. So we're going to need two Ags to form. So it's going to be Ag2Cr4. That'd be the correct formula. So A is wrong. Like the other answer choices, H2Ce2O4 this is actually correct because this is going to be the two hydrogen ions coming together with the oxalate ion, remember C2O4 minus 2, to form oxalic acid. Remember, 8 goes to ic acid, so oxalate will go to oxalic acid. CuPO4, this is wrong because PO4 is phosphate. That's going to be a -3 charge. And copper can't form +3 charges. It can only form +2 or +1. So it'd have to be like something like CO3PO4 2. This would be copper 2 phosphate. This is wrong. Ni, because nickel cannot form +1 charges. So it'd have to be nickel +2 and then C2H3O2 minus and then two of them. And it'd be nickel and then two acetates. So E and D are wrong. This has to be C. Moving on to the FRQ, sometimes you have two different gases that you know are non-cyclic. So they're not ring, they don't have a ring in them. And they have this following elementary analysis. So we can notice how these 2% add up to 100%. So we know that this compound only contains carbons and hydrogens. So if we assume a 100-gram sample of this compound, that means we're going to have 85.7 grams carbon and 14.3 grams hydrogen. So 85.7 divided by molar mass of carbon, which is 12, and 14.3, that's just the molar mass of hydrogen. So it's going to be, molar mass of hydrogen is 1. So it's going to be 14.3 moles hydrogen and 85.7 divided by 12. It's going to be 7.14. Notice how we can pretty much see that there's a 1:2 ratio. It's going to be CH2 as the molar ratio. This is indicative of something like an alkene, because remember, alkenes have the formula CN and then H2N. So if N equals 1 in this case, this is consistent because we'll get CH2. This is obviously an empirical formula. And it says each gas has a molecular weight of 56 plus or minus 1. So that means around a molecular weight of 56. This means plus or minus 1 just means it could be 55 or it could be 56 or like 57, stuff like that. So this plus minus value just represents the uncertainty of the molecular weight. We don't know if it's 55. We don't know if it's 57. Could be any one of those. It says, what are the molecular formula for the compounds? If we look at the empirical formula, this has molar mass of 12 plus 2, that's going to be 14. So to find the molecular formula, 56, molar mass of the entire compound divided by 14, it's going to be 4. That means you have to multiply the EF times 4 to get to the MF. So when we multiply this by 4, we're going to get C4H8. It says, what are the molecular formula compounds? It's going to be C4H8. It says non-cyclic compound. So when we draw the structural isomers for 4 possible non-cyclic isomers with this molecular formula, it's basically just saying draw the isomers. Um, So just drawing the structural formulas, I guess I'm just going to draw them like this. So we have 2 butene right here. We can have butene like this. We can have cis butene, and then we can obviously have this compound as well, uh, like the 2-methyl propene. These are the 4 compounds that are possible. Obviously, it's just kind of just like drawing structural isomers. Um, So that's the answer. And then for this question, calculate the mass percent of carbon in the hydrated form of the solid formula BeC2O4, and then 3 water molecules. You're going to count the water molecules in this molar mass. So beryllium Be, that has a molar mass of 10.8. Sorry, no, has a molar mass of 9.01. So to calculate the molar mass of this is going to be 9.01 plus the 2 carbons, so 2 times 12, plus the 4 oxygens, so 4 times 16, plus the 3 waters. Each water is 18 because there's 2 hydrogens plus oxygen, so 3 times 18. That's going to be the molar mass. And obviously, it says calculate the percent mass percent carbon. Notice how there's 2 carbons, so we're going to have 2 times 12 up here, and then times 100 to get into a percent, and that's going to be our answer. So if we simplify all this, 2 times 12, it's going to be 24, and then 9.01 plus 24 plus 64 plus 3 times 18, which is 54. So 24 divided by 151, which is the whole molar mass, we're going to get around, and then times 100, that's going to be around 15.9%. The answer is going to be 15.9%. It says when heated to 220 degrees Celsius, obviously this is much higher than the boiling point of water. So all this water is going to evaporate off the solid. So it's going to dehydrate and lose its water by this equation. Notice how water is leaving as a gas, water vapor, because it's so hot. That says determine the mass of each product formed, that given that 3.78 times 10 to the 22 molecules of water are formed. So it's a pretty simple problem. 3.78 times 10 to the 22 molecules of water formed. We can see that this equation is balanced, so we don't have to do any balancing. But we know that for every 6.02 times 10 to the 23rd molecules of water, we have 1 mole of water. We know that for every kind of like 3 moles of water, there's going to be, it says mass of each product, so we're going to need the mass of this BeC2O4. First, we can find the mass of water. We know that for every 1 mole of water, because water is also one of our products. So we know that for every 1 mole of water produced, we're going to have 18 grams of water. So 18 times 3.78 times 1022nd, and then divide that by 6.02 times 1023rd. It's me around 1.13 grams H2O. Notice how there's 3 sig figs, so our answer is going to be in 3 sig figs. In addition to that, let's kind of readjust our stoichiometry to calculate the mass of BeC2O4 and erase this. We know that for every 3 moles of H2 we formed, we must have formed 1 mole of BeC2O4. And for every 1 mole of BeC2O4, we know how many grams of BeC2O4 we have. We calculate the molar mass. So it's going to be, again, 9.01 plus 24 plus 64. 1 plus 24 plus 64. We're not including the water molecules anymore because this is just the BeC2O4 without the water. So this is going to be 97.01 grams. So you multiply all this out. We're going to get around 2.03 grams of BeC2O4. So that's our answers. Number 3, commercial brass, alloy of zinc and copper, reacts with hydrochloric acid. It says Cu does not react with HCl, so we know that only this reaction is going to be taking place. Says says excess HCl is used, and this many grams of ZnCl2 is isolated. So that means it's asking mass percent of copper in the original brass sample. This is kind of similar to what you guys did in your lab, just with a slightly different reaction. Obviously, you guys use a precipitation reaction. This is more of a reaction where you're producing hydrogen gas and zinc and chloride ions. Basically, it says determine the mass percent of copper in the original brass sample. So again, that's just the mass of the thing that we're interested in. So the mass of copper divided by the mass of our total sample, which we said was 0.5065 grams, then times 100. That'll get us our answer. So all we got to do now is solve for the mass of copper. We can do that. It says 0.0985 grams of ZnCl2 is isolated. We know that for every 1 mole of Z, or we know that for every how many moles of how many grams of ZnCl2 we'll get 1 mole of ZnCl2. Well, we got to calculate the molar mass of ZnCl2 for that. So that's going to be the molar mass of zinc. So that's going to be 65.38 plus the molar mass of 2 chlorine. So it's 35.45 plus 35.45. So it's going to be 136.28. So for every 136.28 grams of ZnCl2, we have 1 mole of ZnCl2. And we know that for every 1 mole of ZnCl2, we had 1 mole of Zn reacted. And we know that for every, kind of adjust this, we know that for every 1 mole of ZnCl, or just Zn, 1 mole of Zn, we're going to have 65.38 grams of Zn. Now we can't calculate the grams of copper directly because copper is not involved in the reaction. We can calculate the grams of Zn. And remember, the alloy is only zinc and copper. So if we find the mass of the entire alloy, we can subtract the mass of the Zn to find then the mass of the copper. So multiply all this out. 65.38 times 0.0985 divided by 136.28. And that'll get us 0.04725 grams of Zn. So let's do the total mass of the sample, 0.5065 minus this. That's going to be 0.459 grams of copper then in the sample. So then we divide that by the total mass of the sample. And then times 100. So that's going to get us 90.67%. We're given 3 sig figs as our lowest answer, so we're just going to say 90.7%. So that's our answer. Next up, a sample of LSD added to some table salt to form a mixture. Given that 1 gram of sample of the mixture undergoes combustion to form 1.2 grams of carbon dioxide, what is the mass percent of LSD in the mixture? Again, mass percent, we're just going to do mass of the LSD divided by total mass of the sample. So 1 gram sample times 100, that's going to be our answer. So all we got to do is find the mass of the LSD. So it says 1.2 grams of carbon dioxide is produced. If we look at the equation, we have C24H30 and 3O, and that's going to react with oxygen in combustion reaction to form carbon dioxide and water. We don't really need to pay attention to the mole coefficient for the water because we're only given the carbon dioxide. We can really say that this is 24 because all the carbon in the reaction is coming from the LSD. So we know that there's going to be 24 carbon atoms on one side of the equation. There's got to be 24 carbon atoms on the other side of the equation, and that carbon will be in the form of CO2. So balance this out, there's going to be 24 CO2s. So we can say that if we have 1.2 grams of carbon dioxide, so 1.2 grams carbon dioxide, we know that for every 44 grams of carbon dioxide, which is the molar mass of carbon dioxide, we're going to have 1 mole of carbon dioxide. And we know that for every 24 moles of carbon dioxide, we have 1 mole of LSD. And using that, we can find how many grams of LSD we have, because 1 mole of LSD, well, we can calculate the molar mass of LSD. We know that for every 1 mole of LSD, we just add the molar mass of all these elements. So that's going to be 24 times 12 plus 30 for the hydrogen, and then plus 3 times 14 for the nitrogen, and plus 16 for the oxygen. All right, so this lets us calculate the molar mass of the LSD. So we'll just multiply all this out, 24 times 12, and then plus 30, and 3 times 14, and then plus 16. So it's a molar mass of 376 grams. So we know that for every 1 mole of LSD, we have 376 grams of LSD. So if you calculate all this out, you get 0.427 grams. So plug this in for mass of LSD, divide that by 1, and then times 100. So that's obviously going to be 42.7% LSD. All right, last problem. 10.53 grams of an organic compound forms this much water and this many grams of carbon dioxide. So we can say CXHY plus, it says CXHYOZ. So I mean there is some oxygen in this compound. Plus some oxygen, going to be XCO2 plus Y over 2 H2O. We don't really need to care about the balance coefficient of oxygen. We only really need to pay attention to the CO2 and H2O. Because if we find the CO2 and the H2O, then we can find the oxygen afterwards. So it says 9.78 milligrams of water. Divide, we know that for 9.78, we divide that by 1,000 to get into grams. 9.78 divided by 1,000. And then 0.007978. Divide that by the mole mass of water, which is 18. That means we have 0.00054 moles of H2O. And then 23.92 divided by 1,000. Divide that whole thing again by the molar mass of carbon dioxide, 44. So that'll be also 0.00054 moles of CO2. So this is a 10.53 gram sample of an organic compound. And this much CO2 is produced, this much water is produced. We know that there's a, sorry, this should be 1 over y over 2. It looks like a z. But we know that if this much water is produced, that means there's twice as many moles of the compound. It's a 1 to 2 ratio. So, or sorry, there should be double as many moles of hydrogen in the compound. So 0.00054 times 2. That means there's 0.00108 moles of hydrogen in the compound. And there's obviously 0.00054 moles of carbon in the compound. By that, we can find the mass percentages. So 0.00018, that's 0.00108 grams for hydrogen. 0.000, which would be 0.54 times the molar mass of carbon, which is 0. And then times 12, which is going to be 0.00648 grams of carbon. So this is how much carbon. This is how much hydrogen. From this, we can find the mass percentages because then 10.53. We've converted that to grams, so 10.53 divided by 1,000. That's going to be 0.01053. We can subtract the mass of the hydrogen, mass of the carbon, because we know that all the masses together, the carbon plus the hydrogen plus the oxygen, is going to equal this total mass. So we can subtract the other masses, 0.00108, and then minus 0.00648. That's going to get us 0.00297 grams of oxygen divided by the molar mass of oxygen. So divided by 16. So once we divide 0.00297 divided by 16, get the moles of oxygen. That's going to be 0.000186 moles of oxygen. Then we kind of have a molar ratio of oxygen to carbon to hydrogen. So we can kind of just divide by the smallest molar quantity. 0.00054 divided by 0.000186, 0.00108 divided by 0.000186. That's going to be equal 3. So that means it's going to be C3 and then O. When we divide 0.00108 divided by 0.000186, it's going to be around 3, around 6, sorry. So it's going to be C3H6O. So that means it has a molar mass of 116. So let's check. This could be the empirical formula. It could be the molecular formula. So 3 times 12 plus 6 plus 16. That's a molar mass of 58. So that means this is going to be the empirical formula. And this is nice because 116, that's exactly double of 58. So that means we're going to multiply empirical formula times 2. So that means the molecular formula is going to be C6H12O2. So that's our answer. Those are all the solutions. Good luck on your test.